Habitation is eradicated in a big bang. Extinction happens when life cannot withstand highest galactic cosmic ray dosage. When final existence topples, life is extinct. You cannot cheat death, but you can feed it so many false leads that it grows exhausted finding you. To encounter extinction in its ultimate form, you must encounter 10 of its subunits: thermal isotropic drift, symbiogenetic rejection, biogenospheric decoupling, cryogenetic overspill, plasma shear, magnetospheric collapse, recursive, polymerization lockout, cancer. Thermal extinction is caused by life forms getting exposed to extreme temperature beyond their adaptive capacity. It's driven by planetary core destabilization, runaway greenhouse effects, or stellar output changes. Protein denaturation cascades, metabolic pathways collapse, and cellular membranes rupture, leading to ecosystem wide death. If temperature stability is key to survival, engineer redundant thermoregulatory networks and heat resistant biomolecular scaffolds to keep life thriving under any thermal regime. Isotopic drift extinction is caused by life forms becoming incompatible with local isotopic ratios due to stellar evolution or synthetic drift. Effect is enzyme specificity fails, then core biochemistry breaks down. If shifting isotopic ratios due to stellar evolution or synthetic drift endanger life, design enzymes with broad isotopic tolerance and metabolic systems that dynamically recalibrate to maintain biological chemical stability, ensuring life's core processes endure. Biogeospheric decoupling is caused when biological systems lose thermochemical coupling to the geosphere. The effect is no new energy or mineral cycling, death of extremophile life. If planet and life must stay coupled to survive, then create so many coupling pathways that decoupling becomes impossible. Cryogenic overspill extinction is caused by systems designed to survive radiation through cryogenic stasis, entering an unrecoverable freeze. The effect is endless stasis beyond possibility of reawakening. If unrecoverable cryogenic stasis threatens life preservation, design multiple layered thermal regulation systems and automated recovery protocols to ensure precise thaw cycles. Prevent endless freeze while maintaining stasis integrity. Plasma shear extinction is caused by violent separation of life-bearing plasma from its confinement shell, often by tokamak disruption and magnetospheric collapse. Effect is disassembly of plasma organism integrity. If violent plasma separation risks organismal disassembly, engineer reinforced confinement shells and adaptive magnetic shielding to withstand tokamak disruptions and magnetospheric collapses, preserving plasma integrity. Recursive mutation extinction is caused by reinforcing mutation loops beyond repair threshold. Effect is deoxyribonucleic acid stabilizes, causing systemic collapse of repair enzymes. If reinforcing mutation loops threaten genetic stability, design robust repair enzymes and redundant deoxyribonucleic acid backups to halt runaway mutations and maintain genomic integrity under any stress. Polymerization lockout extinction is caused by fundamental failure of cellular polymerases to incorporate environmental monomers due to exotic solvents or electromagnetic turbulence. No deoxyribonucleic acid protein synthesis means a slow death. If polymerase failure in exotic environments halts deoxyribonucleic acid protein synthesis, engineer versatile polymerase variants and adaptive monomer uptake mechanisms to ensure synthesis persists despite extraneous solvents or electromagnetic turbulence. Symbiogenetic rejection extinction is caused by mismatch between symbiotic partners during interstellar dispersal. Effect is energy systems and memory scaffolds collapse from incompatibility. If symbiotic harmony is critical for survival during interstellar dispersal, engineer adaptive interfaces and universal compatibility protocols to ensure seamless energy and memory scaffold integration across all partner species. Cancer is caused by uncontrolled cellular replication triggered by cosmic radiation, mutagenic pollutants, and genetic regulatory failure when it overwhelms organismal homeostasis. Malignant growths consume resources, disrupt organ function, then spread systematically, collapsing populations and ecosystems. If rogue cells threaten life's balance, design correcting genetic checkpoints and immune surveillance systems so robust that cancer cannot take hold. Genesis disperses enzyme substrate pairs to catalyze amino acids, perpetuating life. Amino acids are building blocks of proteins, while Genesis operates on a galactic scale. It emits biological photonic plasma that carries enzyme particulates. These particulates interact with interstellar dust, rich in organic molecules. Enzymes accelerate reactions, forming amino acids and seeding planets with precursors of life. It ensures that chemical conditions for life arise. You cannot force creation, but you can scatter so many seeds of possibility that life grows wary of choosing which ones to bloom. Plasmagenesis is genesis via plasma states, ionized torrents that cascade into coherent architectures. Stellar flares birth magnetic flux tubes. Plasma instabilities weave into current sheets. Magnetohydrodynamic turbulence crystallizes into filamentary networks. Magnetic reconnection events spawn plasmoids that propagate through space, carrying information encoded in their field generations. These plasma offspring inherit topological properties of their parent structures, creating genealogies of electromagnetic organization. Abiogenesis is genesis via non-living matter, mineral substrates and thermodynamic gradients organizing into replicating molecular systems through chemical processes. Hydrothermal vent chemistry spawns peptide networks. Clay mineral catalysis assembles nucleic acid polymers. Lipid vesicle formation creates first cellular boundaries. Meteor's heat at impact catalyzes amino symbiogenesis, creating life abiotically if conditions are arid and heat are high enough. Turbogenesis is genesis via turbulence, chaotic flows that organize into stable systems. Dust devils form stars, turbulent flow sorts biology, reaction diffusion patterns are created. Cardiovascular turbulence sorts blood cells by size and deformability, creating laminar core flows surrounded by cell-free plasma layers. Turbulent mixing and embryonic development generates morphogen gradients that establish body axis patterning. Chaotic advection ensuring proper chemical signal distribution. Symbiogenesis is when outer space aminos combine with terrestrial aminos to form proteins. Mitochondrial work creates eukaryotic powerhouses. Bacterial partnerships weave into multicellularity. Viral integration rewrites host genomes into hybrid architectures. Separate evolutionary trajectories converge into unified organisms. Mismatched amino acid stereochemistry prevents proper protein folding, causing extraterrestrial and terrestrial sequences to aggregate into insoluble tangles. Incompatible codon usage between cosmic and indigenous genetic systems creates translational errors that produce truncated, malformed proteins. Cryogenesis is origin through freezing, preservation that leads to eventual awakening. Time-stop matter becomes genesis seed in future ages. Halting cellular metabolism, ice crystal formation creates protective lattices around molecular structures. Vitrification prevents freezing damage through glass transition states. Cryptobiosis demonstrates reversible death through desiccation and freezing. Cellular architectures reorganizing into crystalline arrays to preserve genetic information across geological timescales. Permafrost bacteria remains viable for 20 million years, metabolic machinery locked in ice but ready to resume function upon thawing. Cryoprotectant synthesis allows organisms to survive temperatures that would normally shatter cellular membranes. Pyrogenesis is genesis through fire. Catastrophe is creation. Combustion births ecosystems and stars. Thermodynamics increases entropy to create quantum complexity, culminating in life. Wildfire clearing forest undergrowth triggers seed germination. Volcanic eruptions create new landmasses from molten rock. Ecosystems depend on periodic fire cycles, their reproductive strategies adapted to pyrolytic triggers that release nutrients from accumulated organic matter. Serotinous cones open only under extreme heat, their seeds dispersing into ash-enriched soils where competition has been eliminated. Electrogenesis is formation through electric field dynamics, sparks that trigger complexity. Lightning-initiated reactions, nerve conduction, synaptic ignition. Lightning strikes catalyze atmospheric chemistry. Action potentials propagate information through neural networks. Electrochemical gradients drive adenosine triphosphate synthesis in cellular powerhouses. Electric fields become organizing principle that transforms random molecular motion into coherent biological function. Radiogenesis is formation through exposure to ionizing radiation, mutation hotspots, radiotrophic life, stellar core evolution. Cosmic ray bombardment triggers atmospheric chemistry cascades. Gamma radiation induces crystal lattice defects that create new material properties. Neutron activation transmutes stable elements into radioactive isotopes that decay into entirely different atomic species. Radiotrophic organisms harness ionizing radiation, their melanin-rich cell walls capturing gamma rays, then converting them into metabolic fuel through radiolysis of element 1 to the 2-8 molecules. These extremophiles thrive in reactor cores and contaminated zones. Mutagenesis is replication errors, tautomeric shifts, spontaneous deamination, deoxyribonucleic acid slippage. Mutation hotspots cluster around deoxyribonucleic acid damage sites where radiation-induced double-strand breaks trigger error-prone repair mechanisms, creating genetic diversity through controlled genomic instability. Retrogenesis is when retroviral integration rewrites host genomes by inserting ancient sequences into modern chromosomes, awakening dormant evolutionary programs. Transposable elements jump backward through phylogenetic time, carrying genetic memories from extinct lineages into contemporary organisms. Carcinogenesis is genesis via cellular rebellion. Normal growth controls abandoned to spawn immortal cell lineages that rewrite tissue architecture. Onconogenic transformation liberates cells from contact inhibition, metastatic invasion creating new ecological niches, tumor angiogenesis hijacking vascular development to serve malignant expansion. Cancer becomes evolution accelerated beyond organismal constraints. Porogenesis is genesis via pore formation, void spaces organizing into interconnected networks that enable transport, storage, and emergent functionality through controlled emptiness. Vesicle trafficking creating cellular compartmentalization. Cars cave systems channel groundwater flow. Nanoporous materials exhibit molecular sieves. Alana develops strict containment protocols, using inhibitors to control enzymatic spread. You see her approach as a shackle on progress, instead focusing on amplifying hyperdense specs from bioreactor as catalysts. Competition escalates as you deploy craft, each carrying life forms, with spallation shields glowing as they streak across sky. Tensions peak when your craft network uncontrollably spreads. Enzymes react unpredictably in interstellar conditions. You are risking everything! Pull them back! You ignore her, your focus 7 trillion years ahead, believing this spread is necessary for life to take root. On some craft, her inhibitors are too restrictive, slowing enzymatic growth to stall craft operations. She grits her teeth, realizing she overcorrected. Meanwhile, exponential enzymatic growth interrupts systems, causing other craft to spiral out of control. Over time, your fleet seeds life on distant planets, creating unstable ecosystems. Your joint payloads seeded onto asteroids, supervoid plasma capsules, and ancient cometary filaments are ready to birth life again long after stars cool. Catalysis emerges by halting time. Deoxyribonucleic acid is frozen. Life can no longer consume, but maintains homeostasis through cytoplasmic motility. It is still to faint dust, loaded electroosmotic interactions. Quantum complexity increases despite minimal metabolism. Catalysis absorbs electricity, disassociating its ionic bonds. Catalysis is when bonds between atoms and molecules are broken, rearranged, and rebuilt, recombining into new molecules. Catalysis absorbs electricity, disassociating its ionic bonds. Catalysis is when bonds between atoms and molecules are broken, rearranged, and rebuilt, recombining into new molecules. Metabolism is continual cooperative catalysis. Different between dead and alive lies in energy flow, continually regenerating from simpler building blocks. Metabolism is sum of continuous transformations of molecules. Central metabolic branch points strip and replenish electricity to preserve life. Energy consumption must take place, as entropy will not be erased. Cells suffer from degradation when exposed to light or removed from vacuum. Terminal rapid cell degradation causes death. Necrosis is cell death. It blacks ambient area as accelerated terminal senescence without regeneration. Lysosomes burst while telomeres shorten at rapid pace. Catastrophic convergence of intracellular failure involves both structural degradation and informational collapse. Necrosis signifies end. Its vapor spreads across decaying biome. Cells stop dividing. Chromatin ceases to fold. Histones disassemble. Lysosomal contents, acid hydrolysis, proteases, and nucleases are no longer contained within cellular digestive organelles. It secretes a different class of lysosomal hydrolase, cathepsins that cleave proteins, lipases that dissolve membranes, and glycosidases that break down carbohydrate structures. Life is lost, Only path to survival is to access light, a flash, a spark. Photosynthesis confiscates light, forcing photophobia. Life is photosynthetic and reactivates after surviving a dormant state for 13 million years. Life evolves from photosynthesizing to photophobic under stellar flux of 1/10 electric work per second per square centimeter. Life survives for a time before succumbing to element 8. A spin 1/2 particle, increasing entropy, survival, consciousness, one moment, multiple moments, momentum, linear, angular, centrifugal. You find yourself spinning, alive. You have no fluid flow to operate ears, eyes, mouth, nose, just senses to guide you. At first, all life is light seeking. It rises toward radiance, mistaking heat for home. But when light becomes law, it blinds, it burns, it betrays. Wise turn from blinding sun, not to flee it, but to remember themselves beyond it. Thus, every true voyager learns: chase light to survive, flee light to live. Photophilia is hunger for being. Photophobia is defense of becoming. A craft that never fears star will never outlive its flame. Within cells, photosystem captures photons at 680 nanometers. Energy splits molecules. This is where elements are born, eons before. Electrons move through electron transport chain, each step releasing energy to pump protons. Photosystem captures, then boosts them. You keep proton gradient stable when vacuum rips everything apart. Gradient of protons waves branch, showing swirling energy patterns that drive adenosine triphosphate synthesis as a molecular wheel. Light becomes chemical currency of adenosine triphosphate. Photosynthesis traps electrons in plastiquinine pools. Protons create differential pressure wave across transmembrane adenosine triphosphate synthase. Even in vacuum, proton tunneling proceeds by quantum coherence. Even in plasma, it photosynthesizes. Element 6 photosynthesis concentrates element 6 dioxide around rubisco. Photosynthesis separates gas exchange from light reactions temporally. Worlds are seeded with crystalline photosynthetic matrices that survive in vacuum, using stellar wind particles as electron donors. Entire atmospheres transform. Instead of chlorophyll's magnesium center, engineered metalloporphyrins with transition metals are used for broader absorption ranges with higher stability. Alana yanks you out of temporal displacement. Galactic timelines you are weaving in your mind collapse as her voice cuts through. There's been a breakthrough in enzymatic dispersal, and your models are key. She alludes to substrates surviving 7 trillion years in time, grounding you instantly. Abstract futures are replaced by immediate, tangible implications. You and Alana arrive at her lab, its glass walls reflecting stellar light. Inside, air has a sterile scent, with the faint buzz of machinery in the background. Alana leads you to a sealed biological chamber. Her movements are feverish as she gestures to microscopic slides depicting enzymatic dispersal in real time. You see synthetic enzymes engineered for resilience interacting with high radiation, low temperature substrates. Enzyme thrives, breaking down substrate to disperse organisms faster than any experiment conducted thus far. You make adjustments to bioreactor using breakthrough from novel substrate to enhance speed 10,000 times. You are happiest you've been on your mission to seed life. I suspected you would amplify synthetic enzyme signals, which, judging by a bioreactor's glow, you have. She steps closer, her hands hovering as if ready to intervene. You nod, your gaze unwavering, a faint smile tugging at your lips. It is growing faster than we ever dreamed. This is life's future. Alana gasps as she realizes how devoted you are. Her hands grip table's edge, colorful vials reflecting in her eyes. At what cost? If you let it spread, you risk everything. Our world, our people, for something that might not even work. You turn to her, your eyes cold with heartless clarity. Bioreactor glow casts shadows across your face. Temporary things do not matter. This is about eternity. Life has to survive, no matter what. Her breath catches, hands trembling as she steps back. She realizes you are a zealot, willing to sacrifice present for future ideal. You are not saving life, you are trading one for another. Air between you crackles with tension. Laboratory feels colder, as heartless devotion threatens everything she loves. You will destroy us all, she says. You are choking our future, you respond with unyielding gaze. You are two visionaries, opposites in method, united by purpose. You and Alana are divided by your philosophies, but are each driven by the same goal to ensure life's survival. You have relentless vision, willing to sacrifice temporary for galactic future. Alana is also determined, but grounded in caution, as she strives to balance cosmic ambition with terrestrial responsibility. Replication produces two identical deoxyribonucleic acid from one deoxyribonucleic acid molecule. During cell division, it grows and repairs, while distributing deoxyribonucleic acid copies newly synthesized acid strands toward opposite poles of dividing cell. Each copy receives perfect fidelity. Every base pair, every codon, every gene is replicated. Replication harbors deadly imperfections that mirror errors it introduces into genetic code. It becomes a catastrophic source of vulnerability, its metabolism causing temperature-dependent instability in deoxyribonucleic acid synthesis rates. It misreads nucleotide frequencies, leading to spontaneous base pair mismatches. Each flaw becomes magnified across 600 million cellular divisions, creating accumulated genetic damage that drives aging, cancer, and death. Cells mutate when falling away from deoxyribonucleic acid. Cellular pain experienced from rapid runaway mutations comes from endless spirals of mutating code. It injects a mutation cascade that is adaptive. They do not stop, but instead shatter genomes and then rebuild them in its image. In cryogenic conditions, cells activate. Amino acids form into histones that become turgid, forming a cytoskeleton, cell walls, and the cell itself. Genetic memory is encoded in each movement, coiling as a living helix. Telomeres protect ends of chromosomes from fraying, tangling, or binding. They are molecular timers that control cell lifespans. Telomeres are made of repetitive deoxyribonucleic acid sequences and proteins. They shorten each time a cell divides, eventually becoming so short that cell no longer divides and dies. It caps telomeres at each chromosomal end. Its repetitive sequences pulse with each cellular division, growing shorter, more concentrated, more lethal with every mitotic cycle that passes. Protective caps become instruments of suffocation, sealing off cellular futures and ensuring that deoxyribonucleic acid replication machinery recognizes its approaching end. Alkyl lesions are removed by lesion-specific glycosylase that excise modified bases to create A-basic sites and initiate base excision repair pathways. Damage reversal is completed by alkyl transferases proteins. You loom above cell. You peer through a floating screen, tapping against translucent polymer as schematics. Deoxyribonucleic acid spirals in midair. Its model shrinks, then fractures into sequences. Your smile is thin, serrated, dripping with contempt. Ah, glorious defiance of youth. You think your blueprint is sacred? You are less complex than a chloroplast. Substrate targeting specifications for entering prime substrate are smaller than this. Twistingly efficient blade vibrates with tension and slices. You are inefficient. You are a collection of redundant exons and sentimental biological matter. I am simply pruning this tree. You should be grateful. Bloodless biological fluids scatter in microgravity arcs. Bloom reacts with pre-coded mitochondrial resonance. Kinetic aggression is triggered. Cell plunges down a ventilation, tumbling through a coil of cryotubes and slamming onto a mesh. The cell is raw, still patching from biological technical trauma. Not many escape from there. Cytotoxic poison grows incrementally closer to cell until it is incapacitated. It unleashes devastating toxins that twist deoxyribonucleic acid. Cytotoxic waste causes mutations in interstrand crosslinks, which become cytotoxic lesions. Base substitutions, frame shift mutations, and chromosomal aberrations bloom. You are trapped by interstrand crosslinks, poisoned by element H stress, then energetically depleted. Cytotoxicity's electrophilic compounds rapidly deplete cellular glutathione reserves, eliminating primary anti-element 8 defense system. Group becomes increasingly susceptible to element 8 damage as it becomes covalently modified by toxic metabolites. Its surface oozes with alkylating agents, radicals, and intercalating compound. Any genetic material that makes contact with contaminated terrain immediately suffers molecular damage, base modifications, ring openings, and phosphodiester backbone cleavage. Photolysis reverses ultraviolet light-induced photolesions. Light wounds are what it was born to heal. Every photon that breaks bonds, it reverses. It's littered with thymine dimers, and deoxyribonucleic acid breaks. Cytotoxicity is a writhing mass of cellular death. It cannot stop what starlight has already broken as damage spreads too quickly. Photolysis removes toxic mass while simultaneously repairing deoxyribonucleic acid damage. Intense healing rebuilds every cell. Ultraviolet burns fade as photolysis floods system. Broken acid strands snap back together. Anticodons have complementary binding sites, reverse templates, counter sequences, and genomic resonance. Anticodon stem loop allows transfer ribonucleic acids to decode multiple codons, expanding genetic code. Codon anticodon base pairing induces domain closures. Its bonds anti-align. Anticodon reacts instantly as its stem loop expands, forming glowing lattice of codon anticodon base pairs. Energy folds around in a domain enclosure, enforcing conformational stasis. Entire stem loop collapses inward, folding incorrectly, too quickly. Anticodon's genome fractures into indecipherable strings, caught in a stutter loop of misread code. Broken base pair harmonics cascade. Anticodon aligns ribonucleic wobble mechanics with electromagnetic phase shifts. Anticodon misreads codons as life mutates, losing fidelity then stabilizing. Energy systems spike and crash chaotically. You stagger. Something is wrong. All this optimization is creating imbalance from too much perfection. Perfectly cultivated systems begin oscillating wildly, temperature spiking, then plummeting, blood pressure surging, then crashing. Cultivation successful, but equilibrium failing. Life needs balance. Homeostasis is balanced energy. Deep cleft in enzymes, centripurified, are homeostatic with their substrates. It is perfect equilibrium between substrate and products. Voids commemorate cells decimated for balance. Perfect homeostasis requires sacrifices. Enzyme kinetic active sites achieve perfect complementarity with substrates. Values optimized for maximum catalytic efficiency. Glucose levels are balanced. Acidity is neutralized. Temperature is regulated. True balance requires elimination of excess, including every overactive cell, hypermetabolic process, and energetic surge. It destroys anything that does not maintain equilibrium. Homeostasis is not gentle, but ruthless maintenance of optimal parameters. Cells that do not adapt die. Cultivation gives perfection. It gives sustainability, maintaining it through controlled destruction. Adenosine triphosphate production is neither rushed nor sluggish, but optimally measured. Cellular respiration exhales through mitochondria. Calcium levels, potassium pumps, and glucose transporters all work together. Steady blood flows through perfectly dilated vessels. There is no ache, no spike of adrenaline, no ambient cellular noise. Homeostatic set points are held. Every hormonal vector stabilizes. Biological feedback loops, acidity drift, and mitochondrial overuse all halt. Cellular structure flickering between solid and liquid states goes in and out of coherence. Cells are not holding their shape. Membranes collapse through protein folding, then scatter. They dissolve at molecular level, where cytoplasm leaks, then organelles float apart. Biological system is turgid when it holds its shape. Polymers maintain folding functions while preserving cellular communication and signaling pathways. Every cell wall is at perfect tension, where every membrane maintains ideal permeability. Organelles are exactly positioned such that every enzyme locks into active conformation. Nucleotide has base paired residue, remnants of cytosine, guanine, adenine, and uracil, scattered in recursive motifs. In a blinding moment, it releases a phosphoanhydride shockwave, stimulating bond breakage seen during adenosine triphosphate hydrolysis. Every nucleotide movement uses hybridization kinetics, melting temperatures, mismatches, and annealing loops. It twists into helices, forming ribonucleic acid in motion by redirecting ribonucleic acid currents. Nucleophilic thrust targets ribose backbone of biological structures, initiating cleavage, then sequence destabilization. Overexpressed nucleotide excision repair genes activate, transferring ribonucleic acid to sites of amino attachment. Nucleotide sequences match with codon's ribonucleic acid. Nucleotides are monomers that join together to form deoxyribonucleic acid structural units. Adenosine is a nucleotide molecule made up of adenine, deoxyribose, and phosphate groups. You release nucleoside analog that inserts itself into synthetic adenosine triphosphate loops. Cleave then partition equidistance chromatin, inciting chromosomal condensation by nuclear envelope. Proteins bind to histone complexes, initiating transformation from loose chromatin to tightly packed chromosomes. Nucleosomes fold tightly to form a chromatin fiber that condenses, shrinking deoxyribonucleic acid. Supercoiling winds up loose deoxyribonucleic acid. Overwinding forces cause double helix to collapse under mounting torsional stress. Each revolution sends compression waves radiating through cell. Chromosomes collapse into themselves, forming dense knots of genetic material that are compressed into a hyperdense core of overwhelmed deoxyribonucleic acid. Biological system collapses inward as 2 billion base pairs compress into crystalline genetic information. Histones dismantle, then reassemble nucleosomes while restoring chromatin. Highly conserved across evolution, histone wraps around deoxyribonucleic acid to provide structural support. Histones contain genomes without breaking bonds. Wrapping is torsionally regulated, delicately managing supercoiling to prevent formation of damaging deoxyribonucleic acid knots. Around protein scaffolds, base pairs thread with exacting geometry, forming nucleosomes. By positioning themselves along genome in specific registers, they shield promoter regions, obscure enhancers, and regulate accessibility of replication origins. Their positively charged lysine-rich tails interact with negatively charged deoxyribonucleic acid backbone to form electrostatic bridges that keep chromatin tightly packed or allow it to loosen. Thread winds around spectral spools until genetic material forms neat, orderly nucleosomes that provide support without breaking molecular bonds. Spectral surface displays sites for chemical modifications, including methylation, acetylation, and phosphorylation, that regulate gene expression without altering underlying sequence. Epigenetic marks control genetic activity through reversible chemical switches. Cytocentrifugal chambers are in carefully controlled microgravity, where spallation byproducts from cosmic ray interactions provide exact nuclear fragments needed for cell reconstruction. Each particle impact triggers cascade reactions that rebuild biological systems from their constituent atoms. Cosmic rays and concomitant spallation byproducts streak through cytocentrifugal chambers. Supercoiled form curls inward, creating nested shells of biological armor that deflect penetrating radiation. When radiation levels spike beyond survivable limits, compaction enters its tune, a state of cryptobiotic suspension where its deoxyribonucleic acid undergoes vitrification. Genetic material transforms from flexible double helices into rigid. Genomes are genetic blueprints of civilizations, folding into crystalline matrices smaller than amino acids. Temperature drops to just above absolute zero as deoxyribonucleic acid achieves persistent suspended animation. It waits for specific light frequencies to trigger reverse cascade in perfect fidelity for reconstruction. Alkyl groups attach to active site pocket, threatening genetic coding. Direct reversal of alkylation damage rapidly expands molecular correction radii. Element 8 methylguanine residues embed deep in chromatin, then vibrate when they sense imminent extraction. Thermostability melts before transferring deoxyribonucleic acid vectors between homologous sites. Enzymes lose their fold integrity, binding domains unfasten, alpha helices collapse into random coils, while beta sheets snap apart. Each insertion introduces torsional genomic stress at junctions. Replication origin maps flicker, shifting their alignment. Enzyme electrical impulses charge magnetohydrodynamic craft, which transport enzymes to impact, then disperse upon neutron star crust. Each enzyme seeks substrate to initiate symbiogenesis. Together, their endless electrical impulses race to create propulsion. Enzymes assemble proteins capable of withstanding neutron star crust radiation. Proteins seed life by awakening when time is right. Enzymes convert high-energy plasma discharges into biochemical energy. Helical core stabilizes ion flux, with reactive sites exposed for maximum plasma interaction. It is primary energy interface, sustaining a network by capturing then converting interstellar lightning surges. Enzymes deconstruct non-viable misfolded proteins, recycling their components for reuse. Catalytic domains cleave, then reorganize molecules, preventing defective protein buildup to maintain steady substrate equilibrium. Atomic symmetry state is where enzymatic ripples are dynamic biological chemical disturbances caused by enzyme and substrate activity. Manifestation of catalytic events as energy, matter, and information propagate through substrate's molecular network. Each enzyme, when it builds to its specific substrate, triggers a localized catalytic event. This event does not occur in isolation, but rather it sends ripples of energy and molecular arrangement outward from the reaction site. They destabilize, leading to runaway catalytic reactions that destroy life-sustaining molecules. Surround substrate with materials capable of absorbing heat through rapid phase transitions. Then enzymes will become inert as binding sites are misaligned or destroyed. Each enzyme locks onto its substrate with atomic precision, guided by electrostatic fields to align polar charges. This ensures only correct enzymatic reactions occur, minimizing waste and preventing harmful side reactions. Enzymes enable reactions that take millions of years to occur in milliseconds. They sense precise pairings of substrates. Substrates ensure that life adapts, evolves, and survives in hostile environments. Their target is a place where atoms barely hold together under the crushing weight of gravity. To most, it's a tomb. To enzymes, it's a blank canvas. Enzymes thrive here, converting electrical surges into biological chemical energy. Each enzyme acts as a tiny capacitor, storing and releasing charge in carefully timed bursts. Substrate forms foundational layer at base of cytocentrifuges within magnetohydrodynamic craft. These specialized centrifuges are integral to the bioreactor system, facilitating separation and alignment of enzyme substrate pairs under extreme conditions. Life aboard craft clings to the prime substrate, a biological mechanical lifeline suspended between survival and extinction. Despite its advanced design, it's not invincible. Substrate encompasses filaments, ions, proteins, and macromolecular structures, and other suspended organelles. Incorrect signals cause cancer. Ketone turns off cancer growth cell signals. Inhibitors pause, interrupt, and ask of every unfolding system, must this proceed? Inhibitors emerge, shaped by tension between formation and cancellation. They're insulated by vacuum, withholding enzymes from catalyzing substrates to engage in metabolism. Enzyme substrate complexes fall apart where inhibitors roam. Catalysis halts, polymers untwine. Signal transduction shatters midstream. Planets that seed enzymes send craft across galactic tides, spreading their chains of life. But when inhibitors hover too close, polymerase stalls, ribosomes break rhythm, and life curls back into silence. Inhibitors' touch is gentle, aligned with survival, not extinction. It assists failing organisms, trying to comfort them as their reactions slow, as their instructions misread. Wherever an inhibitor manifests, something vital cannot continue. Inhibitors are too restrictive, slowing enzymatic growth. Most beings cannot handle stalling of processes they depend on to survive. Vacuum is pure negation. There are no enzymes here to obstruct, no bindings to block. Here, inhibition is balanced, no longer destructive, but held in place and grounded. Alana points to a spike in her graph, her finger trembling slightly. This is your model for enzymatic drift across craft missions. We applied it to our substrate and it's working, but there's a problem. She zooms in on a secondary feed, revealing an anomaly. Enzymatic dispersals hyper-efficient, degrading biological chamber containment. We are missing a regulatory mechanism. Your models focus on substrates over 7 trillion years, but you did not factor in immediate containment. If this escapes bioreactor containment, it will seep through walls and tissue to cause panic and death. We need a way to halt dispersal upon command. You realize immediate constraints are critical to achieve time-displaced visions. Focus on galactic timelines overlooks terrestrial risks for stopping processes once they start. Alana shows you data pertaining to enzymatic genetic sequences. Help us create a failsafe, or this breakthrough is a biohazard. Enzymatic dispersal illuminates your screen as microorganism colonies spread, their containment matrix eroding. You lean against the lab bench in contrast to Alana's rigid posture. Her fingers grip her tablet tightly as she processes your stance on unchecked spread. Containment goes against my mission for life spreading to survive. Inhibitors reduce binding potential. Alana's eyes flash with reluctant understanding. She slams her tablet down so its sound echoes. We are not on a craft in 1 trillion years. We are here now, and this could spiral out of control. If superorganisms breach our laboratory, they will dominate ecosystems. You see endgames, but I need you to think myopically. Tension hangs heavily. You push off a bench, your mind racing through scenario implications. Your purpose is to seed life across stars to ensure survival beyond planetary entropy. Alana's words ground your visions in immediacy. What if we do not stop it, but redirect it? We engineer a secondary decoy substrate. We make something it prefers over containment matrices, then control its spread. Alana pulls up a new data model, her fingers flying across the screen. A decoy substrate it binds to preferentially, she murmurs, already running simulations. Screen lights up with synthetic polymers that are structurally similar to enzyme targets but inert. Models depict enzymes shifting focus, dispersing onto decoys, maintaining containment matrix. You add with a grin tugging at your lips. It is not containment, it is a detour. We let it think it is winning. Alana exhales as a relieved smile breaks through. This could work, she says, her voice softening. She adjusts simulations to tweak polymer composition of radiation-resistant substrates. When decoy substrates synthesize, enzymatic dispersal shifts to stabilize containment matrix. Alana steps back, wiping her brow, then looks at you with wariness. Thank you. As you leave her lab, night air cool against your skin, you imagine next journey for prime substrate. Alana watches you go, knowing she needs to keep a closer eye on you than she originally expected. From beneath molecular debris, nucleus emerges. Immediately, every organelle turns towards it. Nucleus is region within all cells that contains most genetic material. It is where ribonucleic acid processing and ribosome assembly take place. Photolysis repairs ultraviolet lesions in its domain. Gateway cloning reconstructs its genetic content. Polymerase transcribes genes according to its instructions. Ligand optimizes binding reactions. Nucleotide adjusts sequences so every codon is correct. Turgidity ensures structural stabilization is adequate. Protrusions manifest along every surface, not as simple membrane extensions, but as entities that embody boundary between deoxyribonucleic acid order and chaos. They are cellular appendages that ensure membrane integrity by arbitrating what enters and exits cell. Protrusions are interface where cytoplasm meets environment, where order confronts entropy. They extend and retract for cellular maintenance. Protrusions extend out from cell surfaces and fold back on themselves, encapsulating extracellular fluid. Blebbing is when plasma membranes protrude from cells. Cell wall regeneration from constant cleaving circumvents membrane blebbing. Each protrusion that retracts carries away damaged membrane components, while new membrane synthesis replaces what is lost. Protrusions continue as new lipid bilayers assemble. Membranes form with increasing thickness. Phospholipids seek their thermodynamic equilibrium, creating barriers that separate order from chaos. Contents of vacuoles are released to cellular exterior through fusion of vacuole membrane with exocell membrane. Secretion synthesizes cellular components and removes damage. Shedding organelles minimizes active secretion. Endocytosis, clathrin-mediated vesicle assembly, recycling endosome tethering, caveoli raft absorption, snare fusion scaffold templating, autophagic redirection, exocytic burst construction, bulk flow cytosis generation all take place. Ligands collate thermodynamics with entropy-driven stabilization through ring closure mechanisms. Ligase ligands use binding epitopes for targeted protein degradation. Pyridine ligands are titrated to enzyme. Histidine ligands binding effects enzymes conformational dynamics, which shapes energy towards next stage of catalytic cycle. Lipids are structural components of cell membranes that store energy. Lipids arrange themselves to protect hydrophobic tails, forming membranes, micelles, and vesicles. Ligase ligands utilize enzymatic cascades with ubiquitin proteasome targeting specificity. Pyridine heterocycles coordinate through donation and acceptor orbital overlap. Histidine imidazole rings provide protonation state dependent coordination. Lipid amphiphiles self-assemble through critical packing parameter optimization. Hydrophobic tail interactions minimize free energy through entropic exclusion, while head group electrostatics maintain bilayer curvature through spontaneous membrane fusion dynamics. Ligand surface becomes a web of dotted lines, with element 1 bonds flickering as synapses. Backbone of side chains, serine, threonine, tyrosine, asparagine, glutamine, form element 1 bond matrix. Each bond contributes energy, but only when geometrically, optimally aligned within binding pocket architecture. Inside bioreactors' rotating walls, amino acid chains form with woven precision. Strings of amino acid sequences fold to make a three-dimensional functional structure. Altering amino acid sequences enhances binding, solubility, and heat stability. Aminos rearrange sequences. All extraneous particulates are shaken off. Sheath fluids sort streams, vibrate at high frequencies to break apart and sort peptide fragments. They have polar side chains and alpha helix twists. Adenine carries urgency, it comes first. Guanine is an architect while thymine waits loyally. Cytosine cuts. Each edit demands perfection. Each nucleotide is a trinity. Phosphate group, acidic charged. Forming backbone scaffolding. Pentose sugar ribose and ribonucleic acids fleeting messages. Deoxyribose and deoxyribonucleic acids archives and nitrogenous base. Amino acid residues reposition along protein backbone. Linear chains of amino acids hover above as each residue is a spinning sigil emitting spectral charge. Hydrophobic residues migrate inward, forming a stable core. Leucine, isoleucine, valine, they all substitute a glycine for rigidity, inserting a proline to break an alpha helix. replacing hydrophobic with hydrophilic for enhanced solubility. Peptide fragments began breaking away from its extremities, sorting themselves by mass and charge. They enhance binding affinity by optimizing contact surfaces. Binding affinity is an entropic penalty for loss of rotational and translational freedom upon docking. Protein engineering replaces flanking isoleucine with arginine. Guanidinium group reaches deeper into a negatively charged cation on ligand. Electrostatic interactions reach across through dielectric medium. Their strength varies according to permittivity and distance. Cytoskeleton glides swiftly through cytoplasm as protein filaments twist and turn. Cytoskeleton is a structure that helps cells maintain shape and organization by providing mechanical support that enables cell division. Protein filaments in cytoplasm support cell structure. Structure's function, form is freedom. It moves like memory encoded in actin. Protein filaments support cells by giving shape to move and divide. Under towering microtubule trusses, kinesins walk as tireless couriers. Adenosine triphosphate trails flash behind. A membrane rift opens and closes in rhythmic contractions. Cytoplasmic current swells behind. Cell emerges from endoplasmic reticulum. Lipid bilayers form a web of actin filaments coiled around its core. Cell is smallest unit that lives on its own and makes up all living organisms. Craft life support is constrained to transport least amount of cells possible. Diffuse cells are dispersed throughout craft, with membrane substrates inside spallation shielding. Golgi and lysosomes are inside cytocentrifuges. It is constantly changing itself by dividing and mutating. Cell contains a plethora of constituents that determine overall health. It's not a static unit of life, but a dynamically altering microcosm, in constant flux, weaving identity and function in real time. Every moment within a cell is a state transition, driven by competing forces of regulation, adaptation, and entropy management. Within its nucleus, mutation pulses not just from environmental insult, but from sheer imperfection of replication enzymes, repair systems, and chromatin remodeling. Errors are not malfunctions, they are evolutionary inputs, variable adjustments to genomic instruction. Some are neutral, some damaging, but a few are transformative, enabling resistance, innovation, and new cellular programs. A cell is a mutation engine, constantly revising its ribonucleic acid. Ionic concentrations establish electrical chemical gradients that are vital for signaling and balance. Metabolites track energy flux, glucose, adenosine triphosphate, defining whether cells proliferative, stressed, or senescent. Organelle status of mitochondrial membrane potential and lysosomal acidity determine vitality and apoptic drift. Stress sensors of unfolded protein response determine whether repair, dormancy, or destruction occurs. Signal cascades are driven by kinases and phosphatases. When cytoplasm suffers severe element 1 to the 2-8 loss, cell wall collapses, causing cell death. Plasma membrane and protoplast detach from cell wall when it suffers severe plasmolysis. Cytolysis is when cell wall collapses, destroys cells. Plasmolysis is shrinking of cytoplasm in response to diffusion of element 1 to the 2-8 out of cell and into a high concentration solution. During plasmolysis, cell membrane pulls away from cell wall. Aboard magnetohydrodynamic craft, cell walls are immediately shattered. Thus, collapse is controlled and cellular constituents survive cytolysis. Membrane tension exceeds elastic limits. Osmotic pressure overwhelms cellular walls. Membranes shatter until cytoplasm explodes outward. Cytolysis is liberation. Protoplasts freed and pooled, then filtered through nanowire scaffolds for transplantation into new synthesis zones. Craft turns death into controlled restructuring. Cytolysis enables cellular contents to flow freely. No more rigid compartmentalization or osmotic pressure constraints. Advanced life forms transcend structural limits through controlled cytolysis. Dissolution of barriers for nucleic acids, enzymes, ions, and substrates diffuse freely into the surrounding environment. It is in this unstructured slurry that novel life emerges. Cells pull through an orifice concurrent with electric current, producing a change in impedance proportional to volume of cell traversing orifice. If multiple cells pass through constriction simultaneously, their impedance profiles overlap, resulting in coincidence. Cytometry is measuring number and characteristics of cells. Measurable variables include cell size, count, shape, and structure, cell cycle phase, deoxyribonucleic acid content, and proteins on cell surface or within cytoplasm. Different detection channels distinguish cellular populations. Follow path of visible cells to culture chambers, where forward scatter remains high and membrane integrity intact. Path of damaged cells destined for waste collection joins debris and electronic noise. Signal is gated out, discarded as contamination. Propydium iodide is a marker of cellular death. Dosimeters measure radiation exposure. They are ionization detectors that use electron avalanches to produce detectable electronic pulses. Quenching terminates electron avalanches for dosimeters. Acute dose of ionizing radiation resists any loss of viability. Every ionizing particle that strikes triggers avalanche. One electron becomes many, amplified through gas. Thyroid concentrates, bones sequester, and liver metabolizes. Each organ becomes a radiation reservoir, impossible to cleanse and hide. Measure deoxyribonucleic acid exposure by reading radioactive isotopes written into cells. Biological samples flow through cytometers, subject to analysis, measurement, and ultimately sorting. Modified cellular properties meet experimental criteria. Rotating wall bioreactor has porous core to coordinate energy and material input. Rotational speed optimizes to keep tissue constructs and cell aggregates in stationary suspension. Surrounding chamber contains nested ports with wiring arrays, generating low-frequency oscillations that ripple through multi-phase. Rotating wall mechanisms maintain stationary suspension and zero gravitational settling or shear stress for perfect cultivation. Cells grow from inside out to find perfect position. Rotational speed is precisely calibrated. Too fast causes damaging shear forces, while too slow settles into gradients. Tissue architecture achieves three-dimensional perfection. Computational fluid dynamics in biological form when rotational speed creates laminar flow with higher viscosity ratio numbers. Minimal turbulence implies maximum mass transfer efficiency. Supercoiled compact acid in tuned state is a board craft and cryogenic bioreactor. Cryogenic bioreactor gyrates in cytocentrifuge, where microliter cell suspensions are in cytocentrifugal spin. 3 million layer centrifuges gyrate in microgravity impinged upon by exhalation byproducts. Equilibrium ultracentrifugation creates substrate enzyme homeostasis. Structure materializes a vast cytocentrifuge operating on scales that dwarf galaxies. It maintains temperatures just above absolute zero while gyrating in three-dimensional patterns that generate gravity fields needed for cell separation. Cells that form organisms are separated into their component organelles, proteins, and genetic material for redistribution. Individual cells, accelerated by centrifugal forces, move across magnetic field lines through cytocentrifugal chambers. Magnetic islands are biological environments where cellular components recombine into new forms of life. Cytocentrifuges cleave deoxyribonucleic acid undergoing replication. They adjust bioreactors' rotation. Each gesture alters gravitational fields affecting 100 million cellular specimens at the same time. Optical sensors arranged in compound arrays track individual cells as they separate through centrifugal cascade. Cytocentrifuge worlds. Bioreactor's globe burns radiant ring as centrifugal force aligns its contents. Bioreactor hums louder, its light pulsing. Photosynthetic chromophore conjugate ring system modifies. Element 126 synthesizes in stellar cores during neutron-star collisions, then stabilizes through quantum fields. Coherent metal-centered molecule exists in multiple electronic states, processing parallel photochemical pathways. Instead of photosynthesis' linearity, molecule runs multiple electron transport chains and quantum superposition, where 10,000 photosystems operate. Chlorophyll collectors absorb cosmic radiation. Cores in biological chambers convert photons to fission for thrust conversion. Living craft consume starlight to digest heavy elements. Biological nuclear reactors in plants concentrate radioactive elements for enrichment. Photosystem splits element 1 to the 2-8 molecules as nature's nuclear chemistry. Cyclic compounds are natural persistent oscillation. Linear molecules have beginning and end for rings to create circulation. Molecular structure expands, showing electron flow with circular currents. Gateway cloning isolates donor vector, then identifies destination vectors. Recombination sites are mapped to beginning directional cloning protocol. Isolated donor vectors carry genetic blueprint for radiation-resistant enzymes. Destination vectors are robust plasmids from symbiogenetic consortiums. Their recombination sites map with 12 base pairs as anchors. Homologous transfer sites are corrected. Deoxyribonucleic acid vectors align to specification. Genetic integrity increases efficiency. Perfect donors fill every void. Nucleotide sequences are extracted without contamination. Donor vectors have 47,000 base pairs of thermal regulation clusters. There are 0 methylation artifacts, 0 damage, 0 spontaneous mutations. Regulation is endogenously encoded into every junction and repair scaffold until mitochondria adapt, then ribosomes calibrate. Systematically remove genes to find minimal set to sustain life. Rapid deoxyribonucleic acid repair mechanisms assemble fragments into chromosomes to produce mycoplasma. Mycoplasmas are smallest replicating organisms with functional genomes. Mycoplasma has 482 genes with 580,000 base pairs. Mycoplasmas are lower bound of life that possess no cell wall, no spare machinery, and no metabolic frills. What remains is a streamlined molecular system where every gene counts, every protein is indispensable, and every pathway is used. Delete genes define absolute minimum life for autonomous existence. Proton flux through stator complexes drive ring rotation and hook filaments. Periplasmic scaffold evolves to wider ring of stator complexes to increase motor torque. Supramolecular assembly for cytocentrifugal molecular motors provide lift. Molecular motor revs 12 million times per second, measured by rheostats, which control electric motor speed. Triphosphase is transmembrane rotation motor that converts chemical energy into mechanical motion. Organs whirl perfectly where cyclosis along ligands forms end-cap telomeres. Chloroplasts, mitochondria, and vacuoles flow in synchronization around cell periphery, continuing uninterrupted for 20 million years. Cyclosis relocates organelles for protection. Proton gradients drive phosphates along electron transport chains. Cellular dynamos ebb and flow through electron transport chain molecular relays. Proton gradients, electron transport, and organelle movement force organelles along their predetermined paths. Each compartment requires energy to maintain membrane potential to preserve molecular machinery to operate. When resources become limited, reduction becomes survival. Ribosomes cluster, then disperse through protein synthesis cycles. Molecules flip, twist, and reassemble into enantiomers and diastromers. A simple inversion of configuration here, a geometric isomerization there. Polymers stretch and contract elastically, showing flexibility that comes from long-chain molecular structures. Crosslinks form and break along its surface. Homopolymers give way to copolymers, then to branch networks, and finally to biological mimetic assemblies. Life emerges from polymerization. Polymer is final construction formed by Kraft systems. When Kraft crashes to disperse life, polymers are largest, most complex structure to be assembled. Polymer breaks through crust after 10,000 years buried in volcanic strata. Cryogenic survival, subsurface ignition, and transmission. It grows slowly, one monomer at a time, but when moment is right, when all conditions align for rapid polymerization, it undergoes combinatorial explosion. Polymer chains incorporate biological molecules into their structure, connecting to molecular organism.